Take a guess. What do these chunks in my hand look like? Chicken McNuggets? No. Their common name is yellowcake. This is not the kind of cake you can eat. It is an important raw material in the nuclear industry, chemically known as sodium diuranate. After a series of processing and concentration steps, it can be fabricated into fuel rods, which are ultimately converted into the electricity we use every day. When you think about the nuclear industry, you probably imagine something dangerous and mysterious. But the uranium deposit I'm visiting this time looks like nothing more than an endless stretch of grassland. You can even see local herders grazing sheep right above the ore body. So, how do you extract something as strategic as uranium from a place that looks this ordinary? And how does it become these nuggets in my hand? Uranium, atomic number 92, was forged in the most violent events in the universe, supernova explosions and neutron star collisions. About 4.6 billion years ago, as the solar system formed, uranium was incorporated into the primordial material that eventually became Earth. Once on Earth, it combined with elements such as oxygen and fluorine, forming various uranium compounds. Over billions of years of geological evolution, those compounds concentrated and eventually formed uranium deposits. In fact, uranium is a bit more common than many people think. The average abundance of uranium in Earth's crust is about 2.7 parts per million. In other words, every ton of crustal material contains roughly 2.7 grams of uranium. That's roughly on the same order as metals like cobalt, nickel, and lead. By comparison, gold is far rarer, with an average crustal abundance of only about 0.004 parts per million. But there's a catch. Under traditional mining conditions, the typical industrial cutoff grade for uranium is around 0.05%. That means about 500 grams of uranium per ton of ore, which is roughly 185 times higher than the average crustal abundance before it becomes economically viable to mine. So uranium may sound abundant, but in reality it is extremely dispersed, which makes it difficult to extract. Another key point is that uranium is a highly reactive element. In nature, pure uranium almost never exists underground. Instead, it appears in the form of compounds and minerals. Common uranium-bearing minerals include uraninite, pitchblende, coffinite, and various uranium-bearing micas. For example, the world's largest uranium producer, Kazakhstan, along with places like Wyoming in the United States, mainly hosts sandstone-hosted uranium deposits. In Canada, the Athabasca Basin contains some of the richest uranium deposits on Earth, with the highest ore grades ever discovered. The uranium found there is primarily unconformity-related uranium. Meanwhile, in South Africa, uranium often occurs together with gold deposits. These belong to the quartz pebble conglomerate type. The uranium deposit we're visiting this time is located in Inner Mongolia in northern China. This region has long been known for its abundant mineral resources, and the site of China's largest natural uranium project lies within a vast stretch of desert grassland. The yellowcake you saw earlier comes from this very grassland behind me. But if I didn't tell you there was mining happening here, you probably wouldn't notice anything unusual. This place looks nothing like what most people imagine a mine to be. There are no shafts, no tunnels, no miners working underground. The only visible signs are these yellow, green, and blue boxes scattered across the grassland. Those yellow, green, and blue boxes you see on the grassland are actually the uranium wells. The blue boxes are recovery wells. Their job is to pump the liquid back up after the uranium has been dissolved into it. And the yellow boxes are monitoring wells used to track the condition of the surrounding groundwater. The green boxes are injection wells. They are used to inject the leaching solution down into the sandstone uranium layer underground. These wells are arranged in a honeycomb pattern, known as 6 injection, 1 production. In other words, 6 injection wells surrounding one recovery well, with spacing of about 30 meters between wells. Each mining block has a central control room that manages the system, regulating valves and monitoring the flow of injected and extracted fluids. Around the perimeter, there are also 2 evaporation ponds. A small amount of excess treated water is released here and evaporates into the atmosphere. Not far from here, you can even see drilling rigs still operating, opening new wells in the next production area. This site uses a carbon dioxide plus oxygen in-situ leaching process to extract uranium. It's completely different from traditional mining. There are no open pits, no underground tunnels. In a sense, the mining happens without ever seeing the ore itself. What we've just looked at are the parts you can see on the surface. Next, let's take a look at what happens underground, where the uranium actually goes through the extraction process. First, the wells are drilled about 400 meters underground until they reach the uranium-bearing layer. Down there, besides sandstone, there is also a large amount of groundwater. Through the injection wells, a leaching solution containing dissolved carbon dioxide and oxygen is pumped underground. When carbon dioxide dissolves in groundwater, it forms carbonic acid. This is a weak acid that lowers the pH of the groundwater and helps increase the solubility of uranium minerals. At the same time, oxygen promotes the oxidation of uranium. It converts the lower valence tetravalent uranium in the sandstone ore into hexavalent uranium, which is much more soluble. As this reaction continues, uranium ions gradually dissolve into the leaching solution. The uranium-bearing solution is then pumped back up through the recovery wells. It is first collected in storage tanks at the central control station and then transported through pipelines to the hydrometallurgical plant. Here, the uranium solution first passes through adsorption columns, where ion exchange resins capture the uranium ions. The loaded resin is then sent to a stripping column, where a stripping solution washes the uranium back off the resin. The resulting solution is treated with hydrochloric acid to remove impurities. Next, it goes into a mixing tank where sodium hydroxide is added. Sodium hydroxide provides hydroxide ions, which react with uranyl species in the solution to form a precipitate of sodium diuranate. These precipitates are usually bright yellow solids. After they are filtered and pressed into cakes, they end up looking like small yellow blocks. That's why people call it yellowcake. This is the final product produced at the mine. Right now, the international price of natural uranium is roughly around $70 per pound. Sodium diuranate typically contains about 70% uranium, and since it's uranium, it does emit radiation. But the radiation level of natural uranium is actually extremely low. A pound of natural uranium ore releases roughly about 0.02 millisieverts per day, which is roughly comparable to wearing a luminous watch. I was also worried about radiation, but the engineers at the mine told me that as long as you don't literally eat it like a chicken McNugget, and you wash your hands properly after touching it, it's basically not going to cause any real impact. Next, the yellowcake is sent to a conversion facility where sodium diuranate is converted into uranium hexafluoride. From there, it goes to a uranium enrichment plant and then to a fuel fabrication facility, where it is made into the uranium fuel rods used inside nuclear reactors. These fuel rods are loaded into a reactor, where nuclear fission releases a large amount of heat. The heat turns water into steam, and the steam spins a turbine, which drives a generator to produce electricity. That electricity is then transmitted through the grid. It's the power we use every day. All of it starts from that small block of yellowcake. That's why yellowcake is often called the grain of the nuclear industry. And on July 12th last year, this site successfully produced its very first barrel of uranium. One of the most obvious advantages of in-situ uranium mining is its environmental impact. Unlike traditional mining, it doesn't involve blasting open mountains or digging massive pits. The uranium is extracted underground. The mining areas themselves are leased from local herders and farmers, and normal grazing and farming activities continue as usual. Just now, you may have noticed rows of crops near the wells. Those are corn planted this spring. They've only just begun to sprout. By the time they fully grow, even the wellheads will be hidden among the fields. As we were about to leave the mining area, we happened to see local herders bringing their sheep out to graze. The flock was calmly eating grass right around the wells. If you didn't see it with your own eyes, it would be hard to believe that agriculture, livestock grazing, and uranium mining could coexist on the same piece of land. If you look closely at the entire uranium extraction process, you'll notice something surprising. There are hardly any people on site. In fact, most of the personnel operating this uranium mine are located about 200 kilometers away in Hohhot. If the mining fields scattered across Inner Mongolia are the arms of the operation, this place functions as the central nervous system. Inside this control room, operators can monitor uranium production sites hundreds of kilometers away with just a few clicks of a mouse. They can start mining equipment, control the injection wells, check real-time data from each well, and oversee the entire production system. Automation and intelligent control technologies now allow extremely precise regulation of the process. This approach improves efficiency and reduces the need for manual work traditionally required in mining. Mining sites are usually located in remote areas, and the working conditions can be harsh. Recruiting people has always been difficult, and retaining them is even harder. Fewer and fewer young people are willing to work at remote mining sites. One of the engineers here told me that he personally experienced the earlier era of less advanced technology. Traditional mining placed heavy physical burdens on workers, and many families had to live separated for long periods of time. Now, with automation and remote control systems in place, far fewer people are needed on site. Many tasks that once had to be done in person can now be handled remotely. In-situ uranium mining might sound like a pretty obscure term. Most people have never heard of it, but this technology actually matters a lot for the energy system, for the environment, and for the people working in the nuclear industry. As I mentioned earlier, uranium itself isn't particularly rare. The problem is that it's extremely dispersed. Take the Chenjiadian uranium deposit in Inner Mongolia's Songliao Basin. When it was first discovered, experts from Kazakhstan were invited to evaluate it. They spent 3 years studying the geology. In the end, their conclusion was simple. The conditions were too poor. The ore grade was too low. In their view, the deposit simply wasn't worth mining. In other words, the mine was basically written off. But for China, every uranium resource matters. So scientists tried something different. They adopted a third-generation mining method built around a carbon dioxide plus oxygen in-situ leaching process. With this approach, huge amounts of low-grade sandstone uranium that once had no economic value suddenly became usable. And this situation isn't unique to China. Across the world, places like Wyoming, Texas, and Nebraska in the United States, along with Uzbekistan and parts of Australia, all have large sandstone uranium deposits with relatively low grades. With technologies like this, resources that once seemed impossible to mine can suddenly become viable. As of 2026, there are 413 nuclear reactors operating around the world, and 67 more are under construction. For many people, nuclear energy still feels a little scary. But one way or another, fossil fuels are not the end of the story. They're more like humanity's starter pack. Sooner or later, we have to learn how to manage the power of nuclear energy. The real question isn't whether we use it. The real question is how we use it safely and responsibly. When people talk about nuclear power, they usually focus on reactors, cooling towers, containment domes. Very few people think about the uranium mines behind it all. With a steady and persuasive voice, in-situ mining is a quiet technology. You barely see it on the surface, but its impact goes far beyond a technical improvement. It replaces large-scale excavation with underground extraction. Grasslands stay intact. Farmland keeps producing. What it changes is not just the way uranium is mined. It changes the way we live with this source of energy. And as nuclear power gradually becomes one of the basic energy sources supporting modern civilization, the changes happening a few hundred meters underground may quietly shape the future above it.